Good afternoon. I will talk about primarily my approach is focusing on the pore solution and how these common conventional as well as natural pozzolan affecting and mitigating ASR. Uh, so, so pore solution approach, and we know that the pore solution there are the common approach like NIST model is a common approach to estimate pore solution, and where the 75% of the bulk alkali from SEM is considered as a soluble into pore solution, which creates overestimation. Similarly, the James model is really good one to estimate pore solution as a function of replacement level. And extraction technique is a very common technique, but it's laborious. It takes time. You need two machines. You need to squeeze out the solution, and you need an X-ray or ICP to estimate the concentration. So we developed a model, a NIST model, and ASTM C311 based available alkali. We combined together based on the similar principle like NIST model developed, and it works really well to estimate pore solution of the cement and SEM combination as a function of their replacement level. But the ASTM C311 is discontinued. So we try to develop an alternative approach. What about the water-soluble, readily available alkali from the SEM that we use? So you see that cement contributes 75% of the bulk alkali into pore solution. For the fly ash, we use water-soluble alkali. So we use good data set, and we also develop a nonlinear regression model, which really works pretty well for the conventional ash, but we cannot use that model for the alternative fly ash alternatives. So we actually measure it, and this is the ACCT report, which actually use this modified ASTM C114 to measure the water-soluble alkali from fly ash. Then we combine together. That means soluble alkali from cement, soluble alkali from fly ash, combined together give the pore solution as a function of the replacement level. So this is the approach as an alternative we develop, and so we develop an Excel sheet. You give the input. Excel sheet will calculate the pore solution as a function of replacement level. So pore solution, you don't have to extract all the time, because extraction is not a practical way to do it. So we try to develop something, a good solution that we can use in practical purpose. But we actually validated our approach by James model as well as extraction techniques. Here is some of the examples, and you see the NIST model overestimate, but all three kind of similar. So this is an example that we validated based on extraction techniques, James model. Now we use our model to take a decision. So now we have a pore solution, right? We have the pore solution. Now how to estimate the optimum dosage to mitigate ASR? So we develop a parameter in the left side. This is an ASTO standard, our original test, VCMD. We did several aggregate in a different solution concentration, and we develop a relationship called aggregate reactivity versus threshold alkalinity of that aggregate. You see, if the aggregate is R3, the threshold is around, this is a typo, it should be 0.29. If the aggregate is R2, the threshold is 0.34. If the aggregate is R1, the threshold is 0.45. This is common thing, like if the reactivity is slow, the alkali tolerance of the system is high. So that relationship is very fundamental. Now, if we know the reactivity, we can assign a value called threshold alkalinity. Pore solution of the concrete is supposed to be below or pretty close to that value. Then that particular amount of fly ash is good enough to mitigate ASR. That's the relationship we develop. This is called a screening tool, and this is in an Excel tool, and this is also published in TRB. So this is our recommended approach. So you do screening tool, and within 1 or 2 days, get an idea how much you need to mitigate ASR for a particular aggregate with a known reactivity. You got the value step 1. Step 2 is 1567 is a commonly used test, so that data is available. Then compare between these two. If the difference between these two is below 5%, you don't need any further testing. But if the difference is more, then you need a testing. Of course, you can do 1293. It takes 2 years time. That's the practical issue. So we develop a test called ACCT, Accelerated Concrete Cylinder Test. It's It's a very reliable test. It is also an ASTO standard. This is a recently published ASTO standard. We put a 3 by 6 inch concrete cylinder inside a chamber which is surrounded by soap solution. And the soap solution chemistry is equal to the pore solution chemistry of the concrete specimen that we are testing. So it's kind of pretty close. So if the pore solution of the concrete, because SCM sometimes contribute alkali, right? So pore solution will go up, soap solution chemistry go up. If pore solution chemistry goes down, soap solution goes down. So that's kind of equilibrium. So these test conditions allow to detect the soluble alkali contribution from SCM on the ASR. This is a good test, and we use this test. This is done at 60 degrees Celsius, and we measure the length change of the cylinder as a function of time and LVDT data system. And so you see, this is the situation. We know 1567 and 1293 and our test. The only difference is that we do 4.5 pounds per cubic meter. It's not an alkali boosted situation, but 1567 and 1293 is heavily alkali boosted, so we lose the effect of the sensitivity. If SCM is contributing any alkali in a system, it cannot be detected, but we detect it. That's the good thing. And it field mix can be tested. Give me field mix, I make a cylinder and do the test. Here is the success story for the conventional system, Class C and Class F system. We did 22 fly ash. 63% is actually whatever we predicted based on screening tool within 1 or 2 days is supported by the ACCT 75 to 90 days, 1567 14 days. But we're talking about the remaining G2 category where 1567 is underestimating, and we know that, right? 1567 for high alkali situation, maybe for Class C, it doesn't detect the effect of it. So for us, the difference is around 7 to 10%, underestimated by 1567. Now similar approach I use for primarily the natural pozzolan. There are 12 natural pozzolan, 2 blended ash, and 1 reclaimed ash. The good thing is all the natural pozzolan contain significant amount of feldspar and mica. Feldspar and mica contain potassium and sodium. So those crystalline crystalline phase combine the alkali. Those alkali not generally doesn't come to the solution. So that's a good thing, that there are crystalline phase which bounce on alkali. And alkali sulfate, they are very highly soluble. Those alkali sulfate is the primary source of soluble alkali in cement. Those are the primary source in Class C ash. Those are extremely low in natural pozzolan. As a result, this is the thing that we are expecting from the mineralogical analysis. You see that all the natural pozzolan, the bulk alkali is high, 5 to 7%. 65% of that alkali bounded in the crystalline phase, 32 to 70% in the amorphous phase. Now, alkali release, right? Alkali release from the crystalline phase, which is very negligible in case of natural pozzolan. Now, alkali from the amorphous phase can come to the solution as a function of the degree of reaction, but alkali binding is very effective. Alkali binding means what? That pozzolanic reaction produce the extra additional hydration product where the calcium by silicon ratio for the natural pozzolan is pretty low. So the alkali binding, that means alkali coming from the amorphous phase into solution, but at the same time it's binding by the phase, so the net effect is very minimum. As a result, see the alkali release minus the alkali binding equal to the net soluble alkali contribution. So it is negligible for natural pozzolan. Class AFS is very low, but for Class C you see the big difference. For Class C as contribute alkali from the crystalline phase, from the amorphous phase, the alkali binding is not very effective. As a result, Class C as contribute high amount of soluble alkali in pore solution. That makes the difference. And you see here, the left side is water-soluble alkali. Natural pozzolan is very low. Class F intermediate. Class C is high. Our expectation is 14. mineralogical analysis and actual measurements support each other. You see the right side one, available alkali. Natural pozzolan available alkali is still in lower side, but class F intermediate, class C is high. See, it's getting a good spectrum, low to high. Now, these values I use, the available alkali or water-soluble alkali I used in the pore solution model to calculate pore solution. So I'm not taking any decision based on water-soluble or available alkali. I'm putting in the equation to calculate the pore solution. And here you see the pore solution. See the natural pozzolan pore solution on the bar, and the horizontal green dashed line is the threshold of a particular aggregate. It is a highly reactive fine aggregate. You see here the pore solution going down with increasing replacement. And you see 25 to 30% natural pozzolan is good enough to mitigate the ASR of that fine for the highly reactive fine aggregate. For class F, you need 30 to 35. For class C, you need 45 to 50%. So this is the prediction based on the screening tool. Now, this is another important. Suppose aggregate reactivity is also changing. The top line is R1, where the threshold is 0.45. Now R2, that's what we tested, 0.34. For R3, very highly reactive aggregate, it is 0.29. When the aggregate reactivity is extremely high, your percentage of replacement should increase. As for example, see the natural pozzolan for R2, 25 to 30 is good enough. But for R3, you need to increase your replacement level maybe up to 40%. Similarly, class F, similarly, class C. So our way, you can capture the reactivity of the aggregate and the fly ash characteristics. Fly ash characteristics means how it modifies the pore solution. These two fundamental characteristics we apply to calculate how much you need to mitigate ASR. The good thing is, all the natural pozzolan, we did prediction. See the column, the CST prediction, 1567 prediction, and the ACCT prediction, all are supporting each other. None of them failed, all, 100%. That's a good thing for natural pozzolan. For the blended ash, of course, we have these values, ACCT values. For reclaimed ash also, it's pretty good results. So the conclusion here is, the applications of the CST was validated to determine the dosage of the natural pozzolan for ASR mitigation for highly reactive fine aggregate. All the natural pozzolan are alkaline, but it doesn't contribute as a soluble alkaline to pore solution. The water-soluble alkali trend is matching with the percentage. NP is 25 to 30. Water-soluble alkali is low. Class C as water-soluble alkali is very high. Replacement level is also high. That's an interesting. CST predicts the optimum dosage for ASR mitigation for all the studied NPs were validated by the 1567 and our ACCT test. Although AMPT is not recommended for high alkali natural pozzolan, however, because of the water-soluble alkali and available alkali are low, probably you can use it. So this is we developed something that you can use quickly. 1293, 2 years time. So that's why we developed this approach. It can be done rapidly. That's our approach. So, however, we only address ASR. But I'm working, this is the 6-year project with Texas DOT. We developed this whole aspect of this is we develop an Excel tool. You give input. It calculates based on CST how much you need for ASR. It also calculates number shrinkage-based cracking potential. It also predicts the river corrosion. It also predicts the freeze durability in terms of kind of critical saturation. But this is the reactivity section, so we also measure reactivity. And so I will present the data quickly. So see, this is the data of reactivity. This is not my expertise. Here, a lot of experts are sitting here, but we did the measurement based on R3. And also, Pranay is also helping to do the modified R3. The data is not yet available, it is under progress. See that all the natural pozzolan belongs to less reactive pozzolanic category. N4 and N7 is actually one of the calcine clay, one is metakaolin. This is belongs to more reactive category, but they are pozzolanic. Now, how to use this material? How to use this? This is our future. We are thinking how the reactivity and ASR can be connected. If we can, this is our aim. We are going to develop this kind of relationship, like say the pozzolanic. And you see the metakaolin give a good pozzolanic reaction, low CH8 ratio, and alkali binding is very prominent. So if you use the alkalinity of the pore solution very effectively, you need lower quantity. But class C as add extra soluble alkali, increase the pore solution, so you need more quantity. So there is a relation. Class C as more, metakaolin less, class F and natural pozzolanic. If we can develop this kind of relationship based on huge number of materials, then this can be very useful as a supporting tool for whatever the scaling tool that we are predicting very early can be supporting tool, and our determination of the dosage prediction can be more reliable without doing ACCT based concrete test. That's the future. So you take the decision during mix design stage with a good amount of reliability. But of course, I'm not saying the 100% answer. But if you have a bunch of material you already tested, it's probably going to work in future. Not right now, but in future it's going to work. That's our expectation. And we'll continue testing, continue generating this data. This is the thing already for I'm going to implement in the real world project to validate it. So we are going to apply the same tool for this natural pozzolanic on all the alternative materials and see all the major durability, where it stands, how the reactivity and durability connected, those things will be done. That's our future. And these are my sponsors. And thank you.